Hello everyone, my name is Veronique Perdereau. I'm a professor at Sorbonne University. I'm doing research on dexterous robotic manipulation at EASY Lab. First of all, I'd like to warmly thank the organizers for inviting me. I'm so sorry that we cannot meet today. I'm going to talk about multimodal planning and control for dexterous manipulation of challenging objects. I will mainly share an analysis of the challenges arising in complex manipulation tasks that a robot system is asked to execute, and discuss on planning and control solutions that help the robot manage with them. When we look at manipulation tasks, there is, of course, this very first one, where the robotic gripper is taking the object to manipulate. But there are basically two main other tasks. Should it be a tool or anything else to be used for purpose, the object will be placed somewhere else or assembled with some other pieces. The complexity in these tasks is increasing not only with the number of actions to perform to make the task successful, but also with the dependency between actions in the sequence. In fact, when we first grasp the object, the grasping configuration only depends on the object shape and accessibility. But when the object is to be positioned on a palm, then the initial grasping configuration must take into account the destination pose. And this is getting even worse when the object is to be inserted in another one, as the grasping configuration must then allow the insertion motion. To prepare the robot system for the execution of complex manipulation tasks, a three-level planner is required. At the task level, the planner will decompose the task into elementary actions. Those elementary actions will be translated by the action level planner into robotic skills, taking into account the previously described interdependencies between actions. And the motion level planner will take the real-world contingencies to adapt to previously planned robotic skills. More precisely, at the task level, the planner will determine the sequence of actions that are required to complete the task. This can use the expert knowledge through learning by human demonstration or from robotic self-exploration. Actions are separated by specific contact states between the robot and the object. So let's look again at the main tasks that I introduced. They all show a clear decomposition of actions between contact states. The objective of the action level planner is to determine between those contact states the proper movements of the robot, that is, the position and orientation of the arm and gripper, and the force exerted by the arm and the gripper, all of them depending on time. I'm going to show you now the transcription of the previous tasks into robotic skills. For the pinking task, the desired grasp configuration, that is the fingertip locations on the object surface, will be the ultimate goal for the trajectory towards the object and the forces to take it while preserving its integrity. For the stacking task, the first set points to determine will be the desired object pose and the environment or the pile, as it will condition the trajectory and maximum force to come into contact with the environment. Finally, for the assembly, the main concern is the object motion for insertion. Again, this will drive the computation of the arm and gripper trajectory and the maximum force exerted at the interaction level. Those generic robotic skills will be executed by the robot system through a multi-sensor control architecture, where the information coming from many different sensors will be processed to control the pose and the forces everywhere needed. There will be a lot of uncertainties during the execution of the movements. They will be managed by the motion level planner. It will take into account the additional constraints that come from the complete knowledge of the scene, either the environment or the object, or any other unexpected event that changes the contact state. The planned trajectories of forces should be modified in real time accordingly. This is already not easy, but the manipulation tasks become even more challenging when the object is no more rigid. For this reason, handling deformable materials is the main objective of the Sorbonne European project coordinated by Sigma. A very nice consortium is presently developing solutions to scenarios submitted by industrial partners from the toy, footwear, textile, and tire industries. Those study cases all fall into the categories I explained before. As an example, the assembly of tires at Michelin premises or of textile components for Decathlon clothes corresponds to piling layers of materials. But there is a big difference here, as deformation is part of the job. The elastic material must be shaped to the tire or the tension of the fabric kept constant. Looking back to the robotic skills engaged in such task, there is an additional action to perform to deform the party along the positioning. To reach the desired shape, locations of the fingertips and distribution of the forces must be found. The assembly of dolls is very similar. The deformation of the arm is needed to allow insertion in the body. Deformation control is definitely key. Our strategy is to find forces to be exerted at specific locations by the gripper fingertips so as to control the deformation during the execution of the manipulation task. These can be viewed as shape shadowing. The main challenges are first to obtain an estimation of the shape during the deformation, and second, to determine contact locations and forces that cannot be considered separately because they depend on each other. Forces cannot properly deform the shape when they are exerted at wrong locations, but locations cannot be found without knowing the forces required to deform the shape. We therefore propose to iteratively place the fingers at estimated best locations and compute the forces accordingly. The industrial scenarios considered in the Sorbonne project include an additional task that is slightly different from those already presented. This is the molding a doll component or a shoe sole. Instead of inserting a piece, the robot system has to extract a piece from another. These particular cases, the extracted piece is in a soft material, that is, it will deform during the extraction. This adds the difficulty of finding the extraction trajectory, taking into account the deformation. But the main difficulty is to find the pulling force profile that will make the part exit the mold, that is, compensate for the unknown stiction force. The strategy developed in the team is to learn force profiles from human demonstrations of unmolding objects. These force profiles depend on object elastic properties. Evolutionary algorithms are used to generate a diverse repertoire of open-loop policies. Those policies will be adapted online thanks to observations of real-world data, allowing the generation of new sequences of policies. I would have been more than happy to interact with you and answer your questions. This is unfortunately not possible. I thank you very much for your attention.